Hello everyone, my name is Mrs. Morera. In this video, we'll be talking through each of the problems in this year's AIME I competition. One of my absolute favorite lessons to teach is the debriefing after a competition when a student does really well. I've been going through these problems with several students this week, and so I hope these tips and tricks help you too. I will add timestamps to the video so that way you can focus on whichever problems are relevant to your current math level. Starting off here with question number one, we can see in this question that we have a bunch of rates, we have a bunch of times, and we are asked to find the distance. That immediately leads us to using the formula distant equals rate times times. Now, as we're doing this, you might be thinking, well, we have different rates and different times. That's true, but they all have the same distance. So that tells us we have the equation Patrick's rate times Patrick's time equals Tanya's rate times Tanya's time, which equals Jose's rate times Jose's time. Now, what's also nice here in the problem, we are actually given Tanya's information in terms of Patrick's, and then we're given Jose's in terms of Tanya's, which means that we can't express Jose's information in terms of Patrick's information. Therefore, we can rewrite all these variables in terms of RP and TP. And once we've done that, then I'm just solving this without the subscripts because I can write it all in terms of Patrick's times. Then I make two equations, equation one, equation two. Two equations, two unknowns, solve for the variables. Once you have the rate and the time for Patrick, you can then use that to compute the distance, and that concludes this question. So again, big takeaway for something like this. When we're doing this question, you see distance, rates, and times, immediately thinking distance formula. If you feel like you have too many variables and you're solving a system of linear equations, the question has to be well-defined in order to have a well-defined distance. Therefore, you need to be able to write some variables in terms of others, and that will also help keep the algebra simpler as you go. Moving right along to question number two. A popular approach that totally does work, by the way, would be doing the casework on the length of the number and then using stars and bars to finish from there. Totally works. I actually think that an alternate solution to this is going to be the more efficient method. And I get the solution path from the same way I would approach a palindrome question for a coding competition. For example, USACO, which, if you're not familiar, is the USA Computing Olympiad. A similar question to consider looking at if you haven't already is from last year's USACO Cycle, cow checkups. It's in the bronze division, so totally approachable without having to know the higher level techniques. But what's interesting about cow checkups and other similar palindrome questions is that for the coding contests, we really care about keeping the computational complexity simple. And obviously for AIME, we aren't worrying about running this on arbitrarily long palindromes. We aren't doing this for exceedingly long numbers. We are doing it by hand. But the reason why keeping the computational complexity down is still useful for doing calculations by hand is because if you're like me and you make silly mistakes along the way, you want to have the shortest path possible for the least amount of room for error. So the way that we approach palindrome questions when doing coding is we start in the middle and you build your way outwards. And so that way we aren't having to do one loop for where does the beginning of your number go, one loop for where's your number at the when you get to the end of your number, and then one loop kind of going in between because that duplicates a lot of efforts. Instead, we're kind of building it outwards. And so using that same sort of approach then, let's try to build out our numbers here by picking our middle digit first. Now, we can start with one in the middle and we can do some casework there. If we try putting two in the middle, whatever sum we get on the left-hand side of the two has to be the same as the sum on the right-hand side here. Therefore, we get this 2 times whatever this amount is plus 2, which is even. We want to add up to an odd number 13. So by that parity argument, then we need to have an odd number in the middle. And the reason why we need to have a number in the middle at all, by the way, is otherwise you have some sequence of digits here repeated here. So we have 2 times some amount, which is therefore also going to be even. So here are the different cases, and we only have to go up to 9 because anything past 9 isn't really a digit-based 10. That's why they feel the need to clarify, just so people aren't writing numbers in hexadecimal or anything like that. So we start here with the 1 in the middle. Whatever we do on one side immediately determines what we have on the other side. So instead of writing a bunch of possibilities for both sides and then kind of dividing it in half and making sure we're not double counting or anything, I am literally just going to consider possible orderings of the digits that I can put right here. Now, keeping track of ordering as well as what numbers I'm using at the same time is just asking for a computational mistake. Therefore, instead, I'm going to structure this by first figuring out what digits I can even put in this chunk over here. And once I've decided what digits I can even put there, then second, I'm going to go through and as a second step, go ahead and add up those numbers together. So we could, keeping it as simple as possible, everything is a 1. Perfectly valid. Then I can have 1, 2, and then as many things less than 2 as possible. 2 twos or 3 twos. Now, in order to come up with another collection of digits, I next have to introduce a 3. Then I could do a 3, 2, and I could do a 3, 3. Moving on to 4, we could do 4, 1, 1, 4, 2, 5, 1, and 6. So these are the different possible collections of digits that I can put on either side of the 1 because we know these are all the different ways to sum up to 6, and 6 plus 1 plus 6 is 13. Let's go through here then and say how many ways can we order these? There's only one way to make everything a 1, 5 places to put the 2. We have 4, choose 2, and that is 6. One way, 4 places to put the 3. 3 factorial is 6 again. No choices. Where do we put the 4? Where do we put the 4? Where do we put the 5? Only one way to just have a 6. Now we're adding these numbers up together. 6 plus 4, these two are next to each other. 6 plus 4 is 10. That's a nice one. Here's another 4 plus 6 is another 10. We have a 5 plus 1 plus 4. So that's another 10. Then we have 1 here and 1 here. So there are 32 of these. What's really fun is the casework with 1 in the center. That one's going to be the longest to do simply because we're adding up to the 6. Because as we go down, we're going to be adding up to smaller and smaller numbers as we go. And what's really fun is this ends up actually just being 32 plus 16 plus 8 plus 4 plus 2. And then there's a 10, there's a 20, 30 plus 32, final answer 62 on this one. So that's why I really like this one, and it even has that self-checking mechanism. If only one of your numbers here is in the power of 2, that feels like a little bit suspicious that something might have gone wrong. And in fact, I actually added up one of those numbers wrong the first time, and I was like, that really doesn't feel right. And I ended up finding that I just forgot to add a 2 somewhere. So that's another thing that I like about this approach. And again, goal for the casework is to keep it as simple as possible and super organized. Moving right along to question number 3. Let's start by taking a look at kind of the top view angle on this problem. Here's our table with radius 200. If we have some smaller circle inside of this, because again, top view, that's how this will look, we can imagine that there's some distance here where we can put the green circle. That's some distance from the center. The center, definitely not out of bounds. It's really around the edges where we're concerned. Don't want to poke out like that, but because of the way the hemisphere is shaped, we might need to be inside a little bit. But there's some distance here we care about. Once we know that distance, it's going to be the same all the way around here. So ultimately, what we actually care about for solving this question is going to be the distance from the green circle center to the table circle center. And that's the actual distance we want. Once we have that radius, we can compute the area of region of points P. And once we have that area region concluded, then we can use that to find the overall ratios and we're good to go. So let's go ahead and take a look at how this looks now from this side angle. Here is our table, and here, let me get the curve. All right, here is our hemisphere around it, circle center. So this is 200. Now, it might be tempting to say, why can't we just put this green circle 42 units away? And that's really tempting. However, if you draw this out with a compass, you'll see that while we aren't passing the exterior here, so like if we're trying to fit this inside of a cylinder, good to go. But the issue here is that we have this little bit that's going to poke out of the hemisphere. So that's why we actually do need to worry about not getting too close to the edge. However, let's just scooch that in just a tad. This sort of thing here, we want there to be a point of tangency here, because if it's not a point of tangency, either we're inside and we have more room to scooch out, or if we're poking out of it at all, then we're going outside the hemisphere. So we're looking for this point of tangency right here. And as we're getting that, then we can go ahead and draw a line here through the circle center to this point of tangency. You can see my circle skills, a little questionable with the drawing, but we have our circle center, leads out to point of tangency. From there, let's go ahead and drop a perpendicular here. And the reason we want to drop a perpendicular here is because this is that distance that we actually want. If we compute this distance x, we are good to go. So, right triangles. Right triangles, we are thinking Pythagorean theorem. We know that this length here is 42 because the radius of the green circle is 42. We don't know this directly. However, we do know that the total here is 200, and we also know that this bit is 42. Therefore, this bit is 200 minus 42. That's enough to solve with Pythagorean theorem, and then from there it is just a bash. So that are kind of the key insights here for question number 3. On to question number 4. The first thing I'm noticing with this is we have a Diophantine expression, so I'm immediately jumping to Simon's favorite factoring trick. Looking at this, I'm seeing an a plus 1 times b plus 1, but there's no constant term, so we're going to have to subtract 1 from the ending. However, even if you are not familiar with Simon's favorite factoring trick, that's okay. You can still derive this expression by using distributive property backwards twice. From this part here, we could factor out a b, leaving us with the expression a plus b times a 1 plus a. In order to make this like an entirely just a product, it would be great if we could factor out another 1 plus a, but we just have an a. So we're going to add 1. Because you can't just like add 1 to an expression and just be okay with that. We also therefore need to subtract 1, so that way we're effectively adding 0. And now that's a perfectly valid rewrite of what we have. Then, if I want this 1 plus a to be a term here, we need something times a plus 1, so that way we can have something times another a plus 1 over here. Let's go ahead and just do 1, because that way we're not changing the value of this expression. Therefore, I can now factor out this 1 plus a, and we are left with a 1 plus b, and then don't forget the minus 1 at the end. So as you can see, we're getting to the same expression either way. Now, once we're here, we want this expression to be less than or equal to 100. Just to make life easier, let's go ahead and add 1 to both sides. So we get a plus 1 times b plus 1, and that must be less than or equal to 101. Ultimately, we are looking for the number of integers that we can acquire with this expression, and we're looking for positive ones only. So therefore, the question is, how many numbers in the list 1, 2, 3, all the way up to 101, how many of these numbers can we get using this expression? Well, the first thing we note here is that a and b themselves have to be positive integers. Therefore, the smallest value we could plug in for a and b here would be 1. If we do that, then we would get a plus 1 is 2, and b plus 1 also being 2. However, notice that they must also be distinct. Therefore, if a is 1, b cannot be 1. The smallest we could get for b in that case would be 2, giving us 3 overall for the second parentheses bit. Therefore, the smallest number we can actually acquire here is 6. 2 plus 3. So therefore, we have determined that 1, 2, 3, 4, 5 don't work, and our list starts with 6. We know that 6 does in fact work. What about 7? So I know that the factorization for 7, let's just switch colors here. 7 is a prime number, so 7 equals 1 times 7. However, we cannot have either of these factors equaling 1 because that would mean a or b has to equal 0. So while we're able to acquire a 7 by making a or b equal to 6, we actually can't get the 1 term. Therefore, not only does 7 not work, but primes in general don't work. This is a very tempting spot to just end it there. You think you got the insight, and you can compute all of the primes using the sieve of Eratosthenes, and then you're all set. But there is actually a little bit more to it than that. As we're noticing that this 1 plus 1 times 7 doesn't work, you could try the next couple numbers. 8 we can do 2 times 4 is valid, and then we get to 9. And we can actually find out in just a second that 9's not going to work. But for AIME questions, sometimes the trick isn't going to be just like the third number. Sometimes it might be further on in the list. So how could we have solved this if we didn't just experiment with a few more numbers? And why would we know we want to do that? Well, for the same reason that 7 times 1 doesn't work, ultimately then, for whatever number n we have that we want to work, n has to have not only 1 in itself, but we actually need two more distinct factors in between a plus 1 and b plus 1. If a plus 1 equals b plus 1, then we are not able to have a and b be distinct. If a plus 1 or b plus 1 simply equals the n, that doesn't work because n pairs with 1. Therefore, any number we have here must have two distinct factors other than 1 in itself in order for this to work. So the primes are all the numbers with two factors, but how many numbers also have three factors? In order to have precisely three factors, we must have 1 and itself and one number in between. If the number in between is composite, then we could break it down into more factors, so that won't work. Therefore, the number in between must be prime. Then, with that prime number, we know that since 1 and n pair with each other, this number must pair with itself for the pairs of factors. Therefore, the number must be that prime number squared. Therefore, not only do we need to remove from this list of numbers all the primes, we also have to remove all of the square primes. That gives us then our final answer, because anything that's not a square of a prime or a prime number itself is going to have 4 or more factors. So now we are confident that we have the right approach here, and there's nothing else we need to worry about removing. So we're going to say however many numbers we have in here. In fact, let's just start the list at 6, 7, 8, up to 101, which is prime. So I guess we could have cut it off earlier. Doesn't really matter. That however many numbers we have there, minus the number of primes we have, minus the number of primes squared we have. That is going to be the number of numbers that satisfy the constraints for this question. Moving right along here to question number 5, it starts by looking a little scarier than the question actually even is. So we're starting here with our points A and B, and AB here is some segment of length 1. Then we're going to rotate A counterclockwise, so down, yes, all right. So down by theta degrees, we want theta to be something acute, and yeah, let's go with that. And this gives us the new point A prime, where this distance is again 1 still because we're just rotating. And then we are going to rotate point B around A prime here by another theta degree. So let's go ahead and that looks about right. And calling this point B prime, and this length is 1 as well. Now, because of these two angles, this immediately gives us here that these two lines are parallel. And once we have that those lines are parallel, we have now produced a nice parallelogram because we have two parallel sides that are congruent. Then we're also given that this long diagonal here is going to be length 4/3. So now our goal is literally just to figure out how on earth can we use this 4/3 in a triangle to ultimately produce this theta here. So one way you can do this, and I know lots of people jumped to this one, is just saying, hey, let's go ahead and look at one of these small triangles here because it's a parallelogram. Therefore, this side length here is 2/3. This length is 1. Therefore, this length is 1/2. You now have enough information. Use law of cosines. Bam, there's theta. Totally works. Another approach, though, that you don't even need to use law of cosines on is let's go ahead and draw a right triangle here using 4/3 because Pythagorean theorem is something that I know how to do. To get this height, it's not super obvious from that triangle, so let's go ahead and make another triangle right here. Now that I've just taken the side, scooched it in, I'm looking opposite from the theta here. Hypotenuse is 1, so this length is sine, so therefore this is going to be sine of theta. Now, to get this width going all the way across, it's going to be 1 plus a bit. The bit's not super obvious, so let's try a new strategy. 1 plus 1 minus whatever this overlappy section is. So Looking at this overlappy bit here, we have a right triangle with hypotenuse 1 again. So this is adjacent to the theta. So this little bit here is cosine. Therefore, to get the total horizontal distance here, it's 1 plus 1 minus cosine theta. So it is 2 minus cosine theta. Then, literally just using Pythagorean theorem on this, we have 2 minus cosine parentheses squared plus sine squared theta equals 1, that equals not 1, the 4/3 squared. And what's really cool then is the sine squared plus this cosine squared. That's going to just cancel out as 1. And then you're literally just left with the cosine term floating around, and you can do some algebra from there. So, very nice and clean for that one. For this question, our first goal is to get this equation to look less confusing. And one thing that jumps out immediately is that the 20th root of something is a mess, so we're definitely going to take both sides to the power of 20. However, that still leaves us with this whole situation, which feels like it should simplify. I don't really remember any exponent or log rules that make that look nice. Maybe some of you do. You can comment below if so. So I'm looking at this, and the only thing that I know that I can take the log 2026 of really nicely is the number 2026 itself. Obviously, we can't just assume that x equals 2020. So the next nicest thing that I can do is 2026 to the power of something. So I'm just going to define u such that x is 2026 to the power of u. Let's go ahead and make that substitution in for x while also taking the power of 20 to both sides of our equation here. X is our 2026 to the power of u. This whole chunk is going to be to the power of something else, and that's going to come by using exponent rules, u times that thing. So I'm just going to write it over here. Log 2026 of 2026 to the u. The u pops to the outside of a log. We get log 2026 of 2026, which is just 1. So this literally simplifies down to u times u, which is very nice. Then, on the other side of the equation, we had this whole deal to the power of 20, and our x here is 2026 to the power of u, but this whole thingy had been to the power of 20, which means that this is the power of 20u. Right away, I'm looking at this and I'm like, wow, a quadratic. I have a u squared term, a u term, and that constant's going to be kind of obnoxious, but I can do that. And what's really nice with having this as an exponent, having a quadratic in the exponents here, is then I know that ultimately the product of all solutions is what we actually want here. So in order to get the product of our solutions here, that's going to be like 2026 to whatever our first thing is. Because it's a quadratic, there has to be 2 of these. Take that whole deal times 2026 to the power of another value for u. The sum of the u's is actually what we want. So then all we have to do is get this quadratic. And now this term here, again, it's going to have a little bit of a mess going on. You're going to have like the whole, well, this isn't 2026 to the power of something. So I just did, when I was solving through, I took the log of both sides, log base 2026 of both sides, that is. And so that way this ends up being kind of an obnoxious constant. But we can still, again, we don't need to actually find all values for u. We only actually care about the sum of the values for u. And once we find the sum of the values for u, then you can just do 2026 to the power of the sum of the possible u's, and that is our p. So that's kind of the first part of solving this question. Then the next part is, once you have your p, how do you finish from there? And p is, let me check what I solved. All right, I claim that p is 26 to the power of 20. That's what I ended up getting over here. So as I'm doing that, I know prime factorization of 26 is 2 times 13. So this breaks apart into 2 to the 20 times 13 to the 20. And now we've simplified this down to a counting question. You can choose 0 twos, 1 2, 2 2, 3 twos, 4 twos, 5 twos, all the way up to 20 twos. So that is 21 choices for how many twos to choose. Likewise, we have 21 choices for how many 13s to choose. And then we just have to do 21 times 21 is going to be 400 plus 20 plus 21, which is 441 for our final answer. So this is kind of a fun combo question. I enjoyed this one. Question number 7 is simple if you've already seen group theory before, and it is very challenging otherwise. So, if you're wondering why there are children out there in the country who know group theory already, a lot of them learned it at math camps. Various prominent math camps do teach group theory at it. So, that is why I suspect there are students out there who do already know the group theory. If you don't recognize this already as just operations on a permutation group, you're going to have a harder time with this question. But the good news is it is still possible. It's just going to be more challenging that way. When we have this onto function here, that means that we need to make sure that these 1, 2, 3, 4, 5, 6s all have somewhere to go. However, in order to make sure that we somehow get back to where we started for every single number, we need to make sure that all 6 of these numbers are still options along the way. So that way, as we apply this function multiple times, we can somehow get there. Therefore, it's not only onto, but it's also one-to-one, and therefore we have a bijective function here. Therefore, we're literally just thinking of different orderings here of the numbers 1 through 6. And you could say, here is some ordering we do where we say, all right, 1 goes to 3, 2 goes to 5, and so forth. Therefore, the total number of functions pi for permutation, not a coincidence, pi, p, that's permutation. All right, so that's why they defined it to be pi. But literally here, in terms of just all the possible functions pi that are one-to-one and onto, there's going to be precisely 6 factorial of those things total. So we have 6 factorial possible permutations. Not all of them have this functionality though. So we could just have the identity function. That's fine with having just a simple 1 cycle. We could also have a 2 cycle because then we repeat that 3 times. We could have a 3 cycle repeating twice, or we could just have it be 6 cycles. So adding up all the casework there, that's kind of tricky to do. However, I think it's much simpler to compute for just using complementary counting yet again, where we say all the 4 cycles and 5 cycles aren't quite going to work. So it's 6 factorial minus the number of 4 cycles minus the number of 5 cycles. So the way that we can have a permutation that has a cycle length 4 is that we have 4 numbers here that are rotating around in a circle, and we have 4 numbers rotating in a circle. Then the other 2 numbers can either be crisscrossed, let me get orange here. Other 2 can be crisscross with each other or stay the same the whole time. So those are the options for the other 2. So there are 2 ways to choose what are we doing with those other 2 numbers. There's 2 ways to do that. And in terms of which guys go here, that's going to be 6 choose 4 because we have 4 numbers we choose to be in that set. Now, it might seem like, well, don't we also care about the ordering here with these 4 numbers? That's 4 factorial different orderings. Yes, we do, but remember there's rotations here. Because if we have, for example, 1 goes to 2, goes to 3, goes to 4, goes to 1, goes to 2, goes to 3, goes to 4, and that's the rotation we have going on here. That's equivalent to if we had 2 goes to 3, goes to 4, goes to 1, goes to 2, goes to 3, goes to 4, goes to 1. So that's going to be ultimately 4 different rotations. We divide therefore by 4 to make sure we don't overcount. We do the exact same logic here for the 5 cycles. We're choosing 5 numbers here that we're going to be pulling out, and then the other number just kind of stays by itself. So 6 choose 5 here, which is simply going to be 6 ways to choose those 5 numbers. Then we have to consider the orderings. There are 5 factorial orders, but divided by 5 rotations. And then the 1 number out here isn't able to do anything interesting, so we just kind of leave it. And then 6 factorial here, that's a 720. 720 minus that whole situation gets you the answer. So, kind of a neat question, especially if you've seen group theory before, really not that bad. But if you found yourself inventing group theory on the test, I can imagine it felt quite challenging. Moving right along here on to question number 8. For this one, the 17 is more clear how to factor out of that. So we are going to get a 17 times 1001. Now, if you've qualified for AIME, you probably already know the prime factorization of 1001 off the top of your head. Otherwise, you can just go, all right, not divisible by 2, not divisible by 3, not divisible by 5, 7. I don't want to do that, but I'm going to do it anyway. But the good news for the 7 is 7 squared is 49, and 49 times 2 is 98. And counting by 98s, then we can get to 980. And then you're like, wait, oh, that's only 21 away. So plus a 21 here gets you 1001. And in particular, how many, so the 49, this is equivalent for the 98. This would therefore be 7 times 14. Then we added a 0, so we add a 0. Then we have an extra 3 sevens there, and therefore we have 7 times 143 is 1001. And then once we have this, now it feels a lot better because we recognize this as 11 times 13 because 1 plus 3 is 4. So, therefore, prime factorization of this whole number is therefore 7 times 11 times 13 times 17, and we have that whole mess to the power of 17. Let's erase this extra stuff now that we got there. When considering this situation and we want to mod by 12, we can actually then think about each of these individual digits. Mod 12, I want this to equal 5. I'm going to then consider each of these different factors in it to be something mod 12. 7 mod 12 still feels like 7, but again, since we're looking for a remainder of 5, 7 plus 5 is 12, so that 7 is actually equivalent to negative 5. So we have negative 5 here to the power of 17. For the 11, 11 is 1 less than 12, so that is simply negative 1 to the power of 17. For the 13, 13 minus 12 is 1, so that is 1 to the power of 17. And then finally for the 17, 17 minus 12 is 5, so we have 5 to the power of 17. And then we have all of that stuff, mod 12, and we want this product to equal 5. Now, we're specifically looking for the number of positive integer divisors, and the way we can choose any integer divisors of this product is literally just by saying, all right, we choose how many negative 5s we want, how many negative 1s we want, how many 1s, and how many 5s. So the total number is then just going to be taking 18 to the power of 4. That's the number of total positive integer divisors, but we want to know how many of them give you a remainder of 5, which therefore means that how many of these things actually give you a product of 5. And what's really cool here with our 5s, note that both 5 and negative 5 squared, 5 squared and negative 5, same thing. That equals 25, which is 1 bigger than 24, which therefore means it's equivalent to 1 mod 5. So, therefore, with our negative 5s and our positive 5s, if we take two of them is equivalent to multiplying by 1 when we're doing it all mod 12. So, really kind of fun property we have going on there. We could choose as any number of ones we want. We could have 0 ones all the way up through 17 ones. So that is 18 ones that we can choose. We no longer care about those. Then we either need to produce 1 1 by having it be an odd number of 5s, or we can have an odd number of negative 5 times negative 1. So we either have to have odd one of these with an even of these, because an even number of negative 5, negative 1 pairings is going to be itself a 5. An even pairing of these is going to give us 1, or we need an even pairing of 5s and an odd pairing here. So we're going to just count those two separate cases together, multiply for the 18 for how many 1s do we have, and that is going to be our answer. And then the divided by 1,000 at the end, that's just, making it fit Amy bubbling. Question number 9 is all about how you set it up. So rolling a dice is hard to visualize. So instead of rolling a dice and having whatever is facing up, I'm going to draw out just the faces of the dice in order. I understand what I am drawing here is not a proper net of a dice. However, this is just an easier way for me to visualize it. As long as I have well-defined boxes in some ordering, that is perfectly valid. So here is my ordering here. Now, I'm going to go ahead and for writing out probabilities here, exactly one face left blank. I'm going to call that event A. All evens are visible. I'm going to call event B. So therefore, the conditional probability we're looking for is A conditioned on B. The conditional probability for this, therefore, is just going to be for probability of A and B divided by the probability of B. And this is basically just the definition. It might be tempting to say, can we do probability of A times probability of B? But that doesn't work here because we don't have independent events. What's happening with the faces of the dice definitely affect other things that could be happening with the face of the dice here. So can't just do multiplication in the top. We has to be A and B. And as we're doing this, the probability of these things is just literally the number of ways A and B happens divided by the number of options. And that whole thing is going to be over the number of ways we can do event B divided by the total number of ways that can happen. The denominators cancel out. So ultimately, we're literally just left with the number of ways we can do A and B divided by the number of ways we can do B. I also recommend, as you're structuring this, to choose as you're doing your count that we have the faces of the dice or they are themselves distinct. Theoretically, I think this is probably doable otherwise, but it just makes your life way more complicated than it needs to be. And you're not making your math that much harder either by making the faces distinct because all the distinctiveness that's going on, that you have extra multiples of whatever, you're going to cancel that out before you simplify your fraction anyway. So let's go ahead then and figure out how we're going to count the number of ways we get A and B. So if only one face is left blank and we can see all the evens, so that is four faces of the dice that are well defined already. Therefore, of the two remaining faces, either the one or the three or the five has to be hidden. So we have three different cases to handle here. We have where the one is hidden, we have when the three is hidden, and we have when the five is hidden. For each of these cases, we're going to then add them together. These are separate cases that are mutually exclusive. So if the one is hidden, then we say, all right, of the other five things going on, which is the blank, the 2, 3, 4, 5, and 6, that are five different choices, five different things going on. And they have 6 spots to put the first thing, then 5, then 4, then 3, then etc. So this is placing everything except for the one. Now, the one can go, and again, the reason why we have a blank here, the times one at the end is just because we can also place the blank somewhere as well. So it's placing 5 numbers plus a blank. Then we had to choose where the one goes. It can go anywhere except for the blank. So then it's times 5. For the 3 hidden, 6 factorial again, but this time the 3 can only go behind the 4, the 5, or the 6. So that's times 3 options here. And then finally, for having the 5 hidden, we can only place the 5 behind the 6. That's one choice. So therefore, for having the A and B, we have 6 factorial times 5 plus 3 plus 1. Moving on to the B. So how many ways are there to place the even number stickers so that they're visible on all the faces of the dice? I'm going to place the stickers in whatever order I want to make my life easier, but then note as I'm doing this, if I place, let's say, an even first, and here's my other even, here's where I'm putting my 4. If I were to then put like my 5 here later, that means the 5's covering it. But if I place a 3 after I place the 4 here, technically these dice should have been getting the stickers on from small to big, so the 4 would still be what's visible here. So I'm going to make decisions in a different order than the order in which we're placing stickers. We can make the order of decisions different than the order of stickers, and that's okay. So there are 6 times 5 times 4 ways to put down your 3 even stickers. So this handles the evens. Now let's figure out what we can do for the odd numbers. For placing the 1 can go literally anywhere, and we can place the 1 wherever, because even if I put the 1 at the same spot as the 4, the 2, or the 6, doesn't actually make any difference whatsoever because the 1 would have been placed first. So 6 choices for the 1. Then, for placing the 3 cannot go on the same square as the 2 because then it would be covering it. But if the 3 goes where the 4 is or where the 6 is, we don't care. So then that's going to be 5 choices for the 3. And similarly, we have 4 choices then for the 5 because it cannot go on the 2 or the 4, but it's okay if it goes on the 6. So we then have that whole situation here divided by 6 squared times 5 squared times 4 squared. You can simplify from there. And that concludes question number 9. Question 10 immediately looks challenging to start, but the good news is that once you've started it, the ending is actually pretty routine. So let's start by looking at the ending then. we're going to be producing some sort of hexagon here, and the hexagon is not going to be regular. We're having some very strange side lengths going on. So the easiest way, therefore, to compute an area of a hexagon that looks pretty obnoxious is going to be doing a coordinate bash. And we can rotate things because we know we're going to be rotating one triangle around a circumcenter. We can do that really nicely by using a rotation matrix. If you're unfamiliar with those, there are some formulas you can memorize that already multiply the matrix out for you. I just think the matrix is easier to memorize. So we're going to be rotating a triangle. And again, rotating a triangle, getting new points, we can do that with a rotation matrix and then use shoelace formula to finish it up. That's going to be the simplest way to comprehend doing the ending. So the question then is, how do we really get these initial points A, B, C in coordinates that are relatively nice places? That is going to be our main challenge on this one. And looking here at the numbers we are given, we can see that 13, 14, 15 feels quite challenging. There's not an obvious triangle that I can think of off the top of my head that involves these numbers. So instead I'm going to say, all right, of these three numbers, which feels hardest? 13 feels the hardest because it is a big prime. Let's start there then. The only triangle I can possibly think about that involves a 13 is a 5, 12, 13 triangle. Therefore, let's go ahead and draw out a 5, 12, 13 triangle. Of course, this is not yet the triangle ABC. In order to incorporate the BC and the CA part here, we're going to need to add a bit either here or here. Unclear which one we're going to want, so let's try both. Let's try putting something over here and see how that goes. 5, 14. Doesn't feel like any inspiration there. 5, 15. Not feeling any inspiration there. No worries. Let's go ahead and try sticking stuff over here. 12, 14. Not seeing anything. 12, 15. Oh, that's a 3, 4, 5 triangle. So that's scaled up by a multiple of 3. So therefore, we're going to want here a 9, 12, 15 triangle. Let's go ahead and draw that in. So 9, 12, 15, right like that. This is our 12. Here's a 15, and here is a 9. Therefore, would you look at that? 5 plus 9 is 14, and we now have our original triangle ABC. So the corner between the 13 and the 14 is going to be B. Between the 13 and the 15 is A, and therefore this one here is C. Excellent. Because we know that the conclusion is going to be doing shoelace on the hexagon here, we want to coordinate bash from the very start, and we have a really nice convenient 90-degree angle here. Everything is on an axis. If we literally just start by plopping in some coordinate grid right here, and from that, very simple to get the locations of each of these points, and you can use those points then to calculate the circumcenter. So that's not necessarily challenging, it's just a little bit of tediousness to get the circumcenter. Now we're going to be next rotating around the circumcenter. There are formulas to rotate around an arbitrary point. I don't have those memorized anymore. So what I did then is I literally just took my entire triangle and I copied over a new version of it where I shifted it all over to the origin. Since I'm showing this now on the computer though, I'm going to just literally shift up my axes here. I'm literally just shifting the axes so that way it's centered around my circumcenter, and therefore I took whatever coordinates I have for the circumcenter, scooched it over to 0, 0, and I shifted my coordinates for A, B, and C accordingly, simply translating everything by the same change in X and same change of Y. Now that we're here, we can go ahead and rotate using the rotation matrix, and the angle of rotation I'm just going to call theta. I don't know what theta is necessarily. I don't know what that number is, but I can use that and when writing out my equations here. So we want A, B, so we want to make sure that A prime C prime, so the new A and the new C is perpendicular to BC. All right, so here I'm rotating, and here is our new triangle, and this is going to be A prime, C prime, and B prime. The angle we have rotating this right here, by the way, that is our theta. So this is our little angle of rotation going from A to A prime. Now, the good news here, because we have that AC is going to be parallel to one of the axes and BC is parallel to one of the axes. Therefore, we know that whatever new coordinate we get for A prime and C prime, we don't know exactly what the X coordinate is, but we know the x-coordinate is going to be equal. So therefore, we have an equation based on the x-coordinates here for a prime and c prime, and we have the sine theta and the cosine theta there. Then we also know the difference in their y-coordinates. So we don't know what the y-coordinates are, but we know the difference in the y-coordinates has to be 15 because the distance between points A and C is 15. So therefore, we have two equations, two unknowns. You can solve for the angle theta that way. And once you have that angle theta, you can just plug it into the formula for points A prime, B prime, and C prime, get all the x and y coordinates. Now you have coordinates for all 6 points of your hexagon, shoelace theorem, and you're done. Moving on to question 11. Seeing this 8 by 8 grid here, I am instantly thinking of a chessboard. Might be a personal bias because I have some unusually good chess players in my life. However, I do think that that is a reasonable connection for test writers to assume that people are aware of the game of chess existing and know how a chessboard looks. So here I have my 8 by 8 grid. I am further inspired of this visual of a chessboard because as we look at the definition of M, we can see that every single one of these summations, we're going to have all of the verticals and horizontals in some order because you could define your I and J in either order. It's symmetrical, so it doesn't actually matter if you define this to be row, comma, column, or if you define this to be X, comma, Y. Either way, we're going to be adding the differences between all consecutive pairs of cells, so whether they be vertical or horizontal. The summation will eventually include both. All the pairs are going to be listed mirrored along this line, but even that we don't actually care about. We just care about how many times are each of these cells going to appear. Starting with some interior cell here. Let's say we have this cell as a big number, hypothetically. If this is a big number, I'm going to write B for big number. Then, in order to make these differences as big as possible, we want to put a small number in each of these places. Small, 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 small. All right, now around each of these smalls, we want to go ahead and make sure that to maximize differences again, we want to surround it by big numbers so that the differences are as big as possible. Right away, this is already looking like a chessboard even more. So not only did I have the 8 by 8 connection, which that could just be, stylistic difference, could be a little reminder or a nudge for the students, but regardless, we don't even need those dimensions. We can see here just this pattern of bigs and smalls is exactly what it takes to maximize the sum. So I'm just going to fill in some more cells here just so that way we can see the visual more specifically, have more squares to point at. Because while filling this with alternating bigs and smalls is most of the work, there is a little bit of other twiddling around the edges that is going to matter. And just to make this abundantly clear, let's add some labels here so we remember the generalized pattern. The shaded regions are going to be big numbers, unshaded regions are going to be small numbers. Now, not every square is going to repeat in the summation M the same number of times. For example, this big number we know is going to repeat 4 times. 1, 2, 3, 4. And those four occurrences, when it reaches the summation, we're going to be having it subtract the small number adjacent to it 4 times. So even without the absolute values there, we can see that this big number will be added 4 times. Therefore, this is also really nice in reducing the summation. And one more sort of insight motivation to consider here, just looking at the summation, there's zero chance you're calculating the summation with specific locations and writing this all out fully within 12 minutes. That cannot be the intended solution. So this question has to be theoretically doable in 12 minutes. Whether or not it takes you more like 20 or 30 during the test itself, sure. But this should be theoretically doable in 12 minutes. Therefore, there has to be a way to cancel out some of these absolute value bars with each other. This is also something that I was thinking of in my mind because there is a similarly complex looking summation happening in one of the USICO Silver questions this recent test cycle. And that was also part of my inspiration on this one here, is that we've got to be able to simplify the summation. We can't possibly be expected to just place all the numbers and then actually go compute this sum term by term. That's not realistic in 12 minutes. So that's already a cool simplification then. We can see that this big number is going to be appearing 4 times as a positive number. And then likewise for each of these smalls around it, we're going to subtract that small number 1, 2, 3, 4 times. Therefore, for all of these interior squares, there's 36 of them. For these 36 interior squares, we have 18 bigs and 18 smalls. We're going to be adding the 18 bigs 4 times and subtracting the 18 smalls 4 times. Let's go ahead and write that out. 4 times 18 bigs summed minus the sum of 18 smalls. That's going to be the very first part here, and that's handling this inner region. Let me, in fact, color code this. So this green region here is going to be 4 times each of these numbers appears. Let's now consider an edge square. If we're looking at one of these squares along the edge, we can see it appears once, twice, 3 times. In all of those instances, since we had a big square right here in the middle, that is going to be big minus the adjacent small. Therefore, the big is going to be added 3 times, and the smalls, by the same logic, we're going to see the small square getting subtracted 1, 2, 3 times. Great. So let's go ahead now and add that to our final answer over here. We're going to be adding to the stuff in the blue region, the green region. We're going to add to it this orange region, which is each of these different edges. We're going to have 3 times, not 23, 3 times. Now we had to count how many we have here in the orange region. So let's take a look at that. We have 6 on each of the different sides here. So 6 times 4 is 24. Therefore, that is going to be 12 bigs summed minus 12 the sum of 12 smalls. And we're going to be adding that in to our total summation. Finally, let's take a look at the quarters. For the quarters, we're going to have 2 small numbers and 2 big numbers. And those are going to be appearing once, twice each. In this corner, because it was a small number corner, we're subtracting it in each of these little highlighted spots. But over here on the other corner, because this is going to be a bigger number, we're going to go big minus small, big minus small. We're going to be adding this one twice. So therefore, for the corners, we're going to be adding 2 copies of what numbers we have here, which is going to be 2 bigs summed minus the 2 smalls summed. Now that we have the summation written out, all that remains is to figure out which bigs do we want to put in which bucket and which smalls do we want to put in each bucket. Given that the green region here is most represented, we're going to want the biggest bigs and the smallest smalls going in the interior of this square. So the 18 biggest bigs, we're going to start counting at 64, go back 18 slots, and then for the 18 smallest we're going to start at 1 and count up through 18. To get this orange region, I actually did it by kind of working backwards by saying getting the green region was relatively clear what numbers to pick, and it was also relatively easy to count these because the multiplying by 2 section, that's going to be the least represented. So we're going to pick the most middling numbers for this region. So 32 is half of 64. So 32 and 33 split the middle. And then we also want to go slightly out as well. So in fact, let's even write these specific numbers. The 2 bigs we want here are going to be 33, and then going just 1 slot out is going to be 34. Then for the 2 smalls here, we're going to then subtract 32 and 31. Therefore, for this orange region, we're going to be counting from 31 through 18, that interior space. And then for the bigs, we're going to be going from 34 to 64, that interior space. If you find you're having an overlap happening as you're listing this out, make sure you have the correct number of numbers in each bucket and really double check your endpoints there to avoid computation mistakes. But otherwise, literally just compute this and you are good to go on this question. Question 12 is great for the older high school students to attempt because the topics needed for this tend to be learned later in high school, but the actual implementation of them is not nearly as bad as question 12 on the AIME would suggest. So for this question, I'm going to treat it purely as a coordinate bash, and the reason I'm doing that is because trying to visualize stuff with spheres and planes, that is going to be kind of confusing to do purely algebraically and looking at it like geometry. There are some students able to do that, and that's wonderful. I think it is far simpler to go ahead and do this with a coordinate bash, and there's going to be a neat geometric observation we make along the way. But starting off, I'm going to go ahead and draw visually, what does plane P look like if we're looking at it top down? So this is plane P that I have here that I'm drawing, and I will put on here A is our 90-degree angle because that's the 90-degree angle. We'll stick that one right at the origin. Then point B is the one that's slightly further, so we'll put point B up here, all right? And then that looks Y direction to me, so we'll go 0, 6. And we have point C here at 4, 0. To calculate the centroid, that is just the center of mass. We're really just taking the average of the 3 points together. You can calculate the average, get the centroid. Once you have the centroid, I'm sure that there are some more advanced techniques that can be used to reflect across the line. I'm not really bothering with any of those. Literally, all I did was say, I can see the slope of this thing because it's just, the y, change in y over change in x, so -3/2. Flip that around, get a slope of 2/3, and slope of 2/3 through the centroid. As we're doing that, what's the intersection point here? And once I have that intersection point, calculate change in x, change in y, add that to this point to get change in x, change in y. Bam, there is our point D. So I figured off the top of my head what these numbers are, but the point is that those are going to be relatively simple to calculate. Once we've got that much, we're now going to stack spheres on top of each of these points. That's where visually this is just kind of hard to do on a sheet of paper. But let's go ahead and rotate this around so we can see a horizontal cross section of what is happening. So again, here is plane P. We have our points here on this plane P. We also have some other plane, and we know that this plane T cannot be parallel to plane P. And the reason they can't be parallel is because it's tangent to three separate spheres here of different radii. So therefore, for this plane T, it has to be something going out on an angle here. And again, it looks visually from the side like we just have two lines that are intersecting, but again, realize that these are two planes intersecting at some line going in and out of the computer screen right over here. And then our spheres, let's go ahead and draw our spheres. That was not a good one. Let's try again. That's a little better. Now, note that some of these spheres might look like they're overlapping each other just a tad. And the reason that's okay if the spheres look overlapping from the side is because it doesn't actually matter. They are forward and back of each other. These are not going to be three spheres that are necessarily in a perfect line. Their circle centers needn't necessarily be in a perfect line with one another. However, as you can see from the sideways view of this diagram, they are coplanar. So the center of each of these circles is going to be within the same plane. Therefore, in order to solve this question, we actually do not have to calculate anything at all about plane T. What plane T does for us, though, is that if you were to drop some perpendiculars here, you end up getting yourself a bunch of similar triangles because this is all the same angle. You can do the ratios here, and you can be like, hey, yeah, these are all in the same plane. Well, once you got in there, great. Now all we have to do then is say, well, what is this plane? I'm going to call this plane R, and I'm calling it plane R because it's the plane defined by the height of each of the radii. So going back over here, we have the radii of 1, 2, and 3. So instead of having our coordinates just in x, y here, we're going to toss in a z coordinate here. And so point B is the one at radius 2. And the z coordinates here, again, we're just getting these z coordinates based on the height of the radius because the x and the y coordinates determine this point on plane P, and then the z coordinate is the radius to give us the point on R. So now we have then 3 points here that are all in plane R. 3 points is enough to define a plane. You can calculate the equation of the plane however you know how to do that. I literally just tossed it into like something x plus something y plus something z equals something, solved a system of linear equations. I know it looks like 4 variables, but the constant terms you can just kind of scale up and down arbitrarily. So I just picked a constant term that felt nice and friendly to make my numbers all come out to be integers. So that's how I got that plane. And once you have the plane then, you also again have this point D. Just toss in R as your z component of point D, and literally you solve for that on the plane and you are good to go. So again, question 12 I think is a really great question to attempt for older students who have already seen these topics at their high school. Moving on to question 13, on the other hand. So this is a really cool question as well. This one I do think has a lot more competition-y tricks. And let me grab the book actually. I was doing this pretty recently with a student. It is in Art of Problem Solving's Intro to Counting book, not even the intermediate. And in the back of the book, when they have all of those different chapters about different tricks with counting in Pascal's triangle, we have this chapter specifically focused on the binomial theorem. And that is significant here because they even tell us in the problem statement itself they were looking at the sum of binomial coefficients of this form. So let's go ahead and write that out. And we get here that 1 plus x to the power of 10,000 equals, if we expand this out with the summation, all the different variations of 10,000, choose k, times x to the k. And we're summing that as k goes from 0 to 10,000. Now, this is not quite what we're given here for S of R, right? So they're a little bit of a different format. However, every single possible value of K is attainable with this formula here where R is going from 0 to 501. So we have the different ways that we can get all the numbers between multiples of 502, and then the multiples of 502 itself, we just loop over the different possible m's. So therefore, we can just rewrite this sum then as a double summation over all the possible m's and r's. But I'm going to write it with the m's on the inside just so that way it more closely resembles the s of r's to see if that's going to be useful for us. And then again, literally just writing out the same formula here with the 10,000 choose k, except this time I'm just writing a slightly more complicated looking k, but nothing else is actually changing. And likewise, as we're doing this x to the k term, we have x to the power of 502m plus r. Ultimately, for this question, then, let's take a look at where are we even going, because this is from the start. But at the ending here, we're looking to see which ones are multiples of the prime number 503. But here we can see we're working a lot with multiples of 502. And so with that, it's not immediately obvious how something in terms of multiples of 502 is connected to multiples of 503, except for the fact that notice here that the 502 is now in the exponent. And that is significant when we're looking at something mod 503, and they even give you the hint that 503 is prime. This leads us to let's use Fermat's little theorem. And if you are not previously familiar with that, it is the notion that some number to the power of 1 less than the prime number mod by that prime number is going to be equal to 1. And that trick is very nice then, because that tells us that this whole chunk right here is going to be congruent to 1 mod 503, which means then that mod 503, this part zeroes out. Therefore, this summation right here, for all the different possible m values, we have the same x to the power of r term. Therefore, this whole summation situation here, all going to the same s to the r term, x to the r term, therefore, this itself is simply our s sub r. So we have our s sub r times x to the r, and we're summing over all possible values of r. And just to be precise about this, we're told that r is non-negative and less than 502, so therefore r is going from 501 all the way up to 5, going from 0 to 501, so going all the way up to, but less than 502. Great. Now, since we're applying a Fermat over here with the exponent, let's go ahead and do the same thing here on the left-hand side. Now, it's not going to come out quite as nicely with 10,000, but it's actually not as bad as it's going to look like it is. I like just subtracting copies of 502 in bulk. So if we were to subtract one copy of 502, it's going to take us a while, so let's add a 0 there. And in fact, let's do that again because 5,020 is basically halfway. And now, as we subtract these numbers from 10,000, we slightly overshoot and get negative 40, but that's all right. Just to get back in the positives, though, let's add back one more copy of 502. Adding those together, we are pretty less than 500, but then two more, so that is 462. So therefore, all of this stuff, and again, I'm writing equal signs. Technically, these should just be congruences mod 503 at this point, but we have here on the left-hand side 1 plus x to the power of 462 that is congruent mod 502 to 1 plus x to the power of 10,000. From here then, let's again use the binomial theorem just to rewrite this whole expression, and we have here that we're getting the summation as 462 choose. I'll just use r again just so we can compare these sides more similarly to each other. and these summations are going to be equivalent. Now, based on the structure of this thing, we might be saying, well, R can only go up to 462, and that's true. But even if we were to define it to go up to 501, just for consistency on both sides of the equation, we end up like this thing is defined for us that this is defined to be zero when the bottom part exceeds the top. So if we're doing this, even if we were to let R go bigger, this situation is defined to be zero if the bottom exceeds the top. Therefore, at a minimum, however many of these terms on the left we know are zeroed out, at least when we're doing this mod 503, but are not zeroed out over here, those are going to be definitely some of the terms we want. So in this case, then we have 501 minus 462. However many terms are in that range is definitely going to be something that is 0 mod 503. However, this does not necessarily say that that's a final answer yet, because hypothetically, there could be some additional terms here that are equal to a term over here for some smaller r that are still going to zero out mod 503. However, because we can write out each of the s sub r's as 462 choose r, we know that this can be written out then as 462 factorial divided a bunch of stuff, and it's guaranteed to be an integer. 562 factorial is going to be a huge number. However, we are again reminded that 503 is prime. Because 503 is prime, therefore it does not have any factors other than 1 and 503 itself. And 462 factorial is the product of all the numbers 1 through 462, notably not including 503. Therefore, 503 is not a factor for any of these numerators. Therefore, it is not a factor in the factorization of s sub r. Therefore, there are no other terms we need to care about, and thus the final answer for question 13 is simply the difference between these two summations. Because again, s sub r is going to equal 462, choose r. If r is greater than 462, then it zeroes out. But there cannot be any term smaller than that because 503 is a prime number larger than 462. Question number 14. Here we have an equiangular pentagon, and unfortunately we cannot assume that we have a regular pentagon. And the reason that is not a safe assumption for this question is because we're also given information about the diagonal lengths relative to the side lengths. And so since we're given some information here with the sides relative to diagonals, it's possible that this combination of information forces it to not be regular. But that's all right. Let's go ahead then and still put in our side lengths here anyway, which might be forced to be different than each other. Ultimately, what we're asked to find is the square of the perimeter, so let's go ahead and write out what that is. We have a plus b plus c all the way through all the sides here, and then we square this expression. As we square it, the first thing that I note that's going to pop out is a squared, b squared, c squared, d squared, and e squared. Well, notably, that is the sum of the squares of the side lengths. In other words, 308. So great, that part's done already. Then we're going to have an a times b, and a little while later a b times a. Each of these crossover terms appears 2 times, so we will have 2 times all 5 choose 2 ways of doing the crossover terms. Let's just speed run writing these guys out. E, now all the b ones. Alrighty. Almost there. All right, cool. Great. Now, looking at these crossover terms, the only information we haven't really used yet is this information about the square of the diagonal lengths. So let's go ahead and draw on a diagonal. The first diagonal that's jumping out at me, as I draw one in, is I say, hey, I see a triangle here where I know 2 of the side lengths and also the angle in between. That is 108 degrees. If you don't already know it's 108 degrees, you're realistically not solving this question within the AIME time limits. Furthermore, not only should you already know 108 degrees, you should also know the cosine of 108 degrees. You might be wondering, why are there children in the country who just happen to know the cosine of 108 degrees? That feels pretty random. I actually did have multiple students who just knew that going into the AIME. And the reason why students just happen to know that number is because if you look at a regular pentagon and phi, the golden ratio, there are some really cool properties you can do there, which is why there are students who just know cosine of 108. So again, if you aren't already familiar with all that cool stuff with phi and pentagons, you're not solving this question, but the good news is that a lot of you watching this video probably do in fact know the cosine of 108 degrees, so we continue from there. Using law of cosine, you can calculate this diagonal length, and it's going to be A times B times a constant. Excellent. So we can therefore get this crossover term plus BC plus CD, and you can see that there's going to be 5 of these. However, there are not 5 things here in our sum. We have 10 things in the sum. So all of these crossover terms that are not consecutive side lengths, those we don't have yet. So that's all right. Let's come up with a new plan. Going back to this first diagonal that we drew in, let's think of another triangle that we can make. I see that E and C both touch that line, so let's go ahead and extend these outwards into another triangle. Since we know this is 108 degrees, 180 minus 108 gives us 72 here. Same logic, 72 here. Isosceles triangle, you can calculate this angle measure here as well. Then, using law of sines, you can go ahead and compute this length here in terms of D, which is equivalent to this length here in terms of D. So we're going to have constant times D, constant times D. From there, let's now figure out how we can get this side length squared. Well, law of cosines worked for me so far. Let's just try doing it again. As we get this crossover term, we're going to see constant D plus E times constant D plus C times some constant that you can calculate because you just know properties with phi. You can do half angle, double angle to get there from the angles you know. Great. Okay. So with this crossover term, we can see what will this produce. We're going to get each of these guys squared again, but that's okay. We know how to handle that. That's 308. We're going to get this E times D term and the C times D term with a constant. But that's okay. We already know how to handle it with these blue lines. We already did those with law of cosines previously. Then, most importantly, we are going to get these EC terms popping out. And by that same logic, all of these guys we can get to pop out of our formula. Once we have all that, now it's just a bash, but we have a plan that we know is going to work. As a fun fact, one of my students actually came up with a really cool strategy, basically just solving the question by focusing especially on this triangle. I'll leave it as an exercise for you for exactly how that was possible. The way I've explained it here is what I think a really standard approach to the question, where it's realistic within 12 to 20 minutes, and it's also something that uses a lot of formulas that students would already know. On to the final question here, question number 15. This is actually kind of a fun finale question to the exam, I think, because if you're qualifying for AIME, you actually can probably solve this question. It's just going to take a while. And the 10 by 10 here, that's kind of a difficult number to start with. So let's start with something simpler, and we can build up our intuition as the graphs get bigger. Instead of trying to put 5 loops in a 10 by 10, let's start small by trying to see if we can put 1 loop in a 2 by 2. So starting very small with a 2 by 2 grid, let's see how many ways we can fill that. Well, the only actual possibility here is having a 2 by 2, just filling up the whole thing, kind of like they have right here. So there's only one possibility for that. One way we can fill a 2 by 2. Great. That was simple. Now let's try a 4 by 4 and see how many ways we can put 2 loops inside of a 4 by 4. As we're doing this, if we start by putting like a 2 by 2 here, then we have this awkward gap. Note that we also can't do any even loops, by the way, because we really want to have even loops only. We don't want any odd loops because of this. So keep that in mind. But if we were to put a 2 by 2 in the corner there, we're left with this awkward L shape that we won't be able to fill. Therefore, if we include a 2 by 2, we have to center it and have a 4 by 4 as the outside bit. So we can have a 4 by 4 with a nested 2 by 2 inside. That is a valid possibility. And because there's only one way to fill a 2 by 2, there's only one way, therefore, to do this case. Next, we could say, what if we stripe it? Again, we cannot do odd number stripes, but we can do even stripes, where we have it go right down the middle. And we could do that vertically, or we could do it horizontally. So that is two different cases to consider here. Therefore, two stripy cases, one circly case. That gives us a total of three possible ways that we can form a 4 by 4. I'm just going to zoom everything down a little bit just so I have more space to write. As you're doing this on paper, though, I do not recommend just writing super teeny tiny. I recommend you just take up a lot of paper, keep it super, super organized. And the more organized you can keep this, the better. Because when you get to your final answer here, you're going to start noticing this powers of three going on as we're building up the cases. But the final answer is not going to be 81. It's going to be slightly bigger than 81, which I know is a trick. And that's why you want to be so confident as you're building up these cases that you don't fall for that trap. Even if you calculate the number correctly, you don't want to just round down and say, oh, I must have overcounted. No, you didn't. You just need to be really confident in that by keeping your work super, super organized. So let's go ahead and start by filling a 6 by 6. So the last two examples, we started by having one of the loops just enveloping the entire space. And if we start with the 6 by 6 loop here, and I'm going to start adding labels as the cases are getting bigger, starting with the 6 by 6 here, and again, this is length 4, length 2, 2, 4. If we start with the 6 by 6 here, we are left with a little 4 by 4 rectangle on the inside. And as previously established, there are three ways that we can form a 4 by 4. So there are three variations of doing the outside loop as a 6 by 6. Going on the other options then, well, if we were to break this up and say, what if we do a stripe? Again, we can only do even length stripes. So let's try having a stripe here where we have a 2 by 6. Note that if we did like a 2 by 4 or something, we're left with an awkward L shape. We could put a 2 by 2 here potentially, but then we have this big gap here that we can't possibly fill with a singular loop remaining. So therefore, we are going to need to go all the way across the bottom here. If we do this, we now have here a 4 by 6 region that we need to fill. If we try striping it horizontally, then we end up getting, let's look at the numbers here, 2 by 4, 2 by 4, 2 by 4. That seems kind of valid, except for the fact that we'd have 4 loops now instead of 3 loops. And we want to try to make sure we're using our space efficiently, because if we were to plop a 6 by 6 inside of a 10 by 10, just thinking ahead a little bit, we'd have 2 more loops outside of that we need to do. And then if we don't have 2 more loops afterwards remaining, then that's not going to work. So we do need to really kind of restrict this to 3 loops and not more than that. So that's why we can't horizontally stripe that. However, we can vertically stripe this and go 2, 2, 2, like so. This is valid. So we can do it vertically. We can also do this horizontally, which means therefore that there are 2 ways that we could do the whole stripey bit. Are there more potentially? Let's keep experimenting. We could try drawing another, let me switch to purple just so I can, again, purple's kind of like my base shape and then I'm filling it in from there. We want to do something that's different than stripes, but we also want to make sure it's different than what we did over here. So we could start by maybe saying, what if we do one stripe? So we have one singular stripe here that is a 2 by 6. Then we are left with this 4 by 6 region. And we have the question, is there any other way we could possibly fill this? So if we stripe it, that reduces to a previous case we've already considered. So we don't want to stripe it. We could say, what happens if we put a little square here? But again, if we put a square there, we know we need 2 loops to fill that square. And so then that would be 2, 3, 4 loops total, but we only want to use 3 loops. So we can't do a square there. But we could actually have a 4 by 6 loop, that's valid. And then we could nest inside of that 4 by 6. We can put inside of that a 2 by 3. And again, this is a 4 by 6 on the outside, 2 by 3 on the inside. That works. That completely fills in our space here. And we can rotate this a few different ways. So as we're doing this, just to make sure we don't accidentally overcount, I'm feeling like you go 1, 2, 3, 4. Now let's do a sanity check for double counting here. We're not double counting because this 4 by 6, we are not filling with stripes. Therefore, the stripy bit is in a unique place for all four rotations. Therefore, we are not overcounting by saying, hey, there's four rotations here. Therefore, for this 6 by 6 case, we have three ways to do nested, four ways to do a 4 by 6, two ways to do stripes, 3 plus 4 plus 6, that gives us 9. Therefore, we have 9 different ways we could structure this 6 by 6. I'm just shrinking this down. Yeah, I don't think I'm shrinking this down. But the good news is that as you could do this on your own, you can do an 8 by 8, then you can do the 10 by 10 case. Obviously, as the cases get bigger, there are more things to consider, but just make sure you're being very systematic and categorize your cases into buckets because the more you can count the number of things in a bucket, the better. Again, notice we're filling 4 by 6 in non-striped ways. That's going to be critical as you start going up to a larger space because if we're doing stripes versus non-stripes, that matters. But if we're putting stripes inside of something that's non-striped already, you might get a new pattern there. So you just want to keep it super, super organized, labeled, and whenever you have a region that reduces it to a problem you've previously solved, refer back to it. So we're kind of building it up recursively in a way. By just building this up all the way to the end, ultimately you can get your 10 by 10 grid. And the answer is again, not 81. As much as it looks like it's about to be 81, it's not. It ends up being a little bit bigger than that. Because if you try proving it's always a power of 3, you should be able to prove it's always a power of 3 if that pattern holds forever. It's not possible to prove that because it's not true. That concludes all 15 questions. I hope that you found this video to be a useful resource. I know it is super exciting when you just finished taking a test in one of these competitions and you just want to see how to solve the other questions to see if maybe you could pick up a few more points the following year. Again, my name is Mrs. Moreira. Feel free to leave comments below if you have any questions about these problems or you have a solution that's better than one of the ones that I provided. You're also more than welcome to email me. I will list my email address below as well. Thank you for watching and have a great rest of your day.